In this video, we're going to talk about Descartes' rule of signs. So, French mathematician Ryne Descartes, if my pronunciation is correct there, found the following relationship between the coefficients of a polynomial function and the number of positive and negative zeros of the function. And here's what he found. It says the number of positive real zeros of f is equal to the number of changes in sign of the coefficients of f of x, or is less than this by an even number. The number of negative real zeros of f is equal to the number of changes in sign of the coefficients of f of negative x, or is less than this by an even number. So let's keep these rules at the top up here, and let's look at our example that we have. We're going to determine the possible numbers of positive real zeros, negative real zeros, and imaginary zeros for the following polynomial function. So you might be sitting there watching this video and thinking, okay, I see positive real zeros. We just read about Descartes' rule right there. And negative real zeros, that was in white. But what about the imaginary zeros? How are we going to figure that out? Well, if we remember the fundamental theorem of algebra, it states that the degree of our polynomial is going to tell us how many solutions or how many zeros there will be for our polynomial function. So if you want to review the fundamental theorem of algebra video, I'll link that in the cards right now. But essentially this tells us, okay, we see a 6 as our highest degree. So we know we need to have 6 possible solutions. Okay? And so whatever we find for positive and negative, if that doesn't equal 6, then we know the rest of those solutions should be imaginary. So that's where the imaginary solutions are going to come in. Okay? All right, so what we are looking for is a sign change of our coefficients. So change in sign of the coefficients. So if we look at our polynomial here, so 2x to the 6th minus 5x to the 5th minus 3x to the 4th plus 3x cubed plus 10x squared plus x minus 9. We're looking at the coefficients, right? So here we have a positive 2x to the 6th and then a negative, right? So we'll go from positive to negative, so that would be one sign change. Negative to negative, negative to positive, so that would be a second sign change. Positive to positive, positive to positive, positive to negative, so that would be a third sign change. So now what this tells us is we either have, so for positive zeros, we either have 3 or less than this by an even number. So our even number would be 2, and so less than that, so we either have 3 positive zeros or we have 1 positive zero. Okay? So now what we're going to do is we're going to rewrite our f of x function, but now instead of f of x, we're going to do f of negative x. So we're going to write f of negative x is equal to 2 times negative x to the 6th minus 5 times negative x to the 5th minus 3 times negative x to the 4th plus 3 times negative x cubed plus 10 times negative x squared plus negative x minus 9. So let's simplify this and then let's look at our sign changes once again. So now we see that we would have, so negative x to the 6th, that's going to result in a positive x, right? Because anytime we have a negative raised to a positive exponent, it's still going to be negative, or excuse me, it's going to be positive. So this is going to be 2x to the 6th. But now we'll have a negative x to the 5th power, so that's going to be a negative x times a negative 5, so plus 5x to the 5th. Negative x to the 4th would result in a positive x. Positive times a negative would be negative 3x to the 4th. Negative x cubed would be negative x, and times 3 would be negative 3x cubed. Negative x squared would be x, so this would be plus 10x squared. This would become minus x, and then minus 9. So now we can evaluate our sign changes once again. So we'll scroll down a little bit, and then you can see our table that we're going to use. So this is a positive, so positive, positive, but we go from positive to negative, so there's one sign change. Negative, negative, negative to positive, so there's a second sign change. And then we go from positive to negative, so there's a third sign change, and we end with a negative. So for negative zeros, we too are either going to have 3 or 1 negative zeros. So now if we go down here to our table, we know that our total zeros should be 6. So all of these should be 6. Okay, so now let's say that we have 3 positive real zeros. So if we have 3 positive real zeros, we could either have 3 negative or 1 negative. So let's just say we have 3 negative real zeros. So that's 6, right? So if that's the case, then we don't have any imaginary zeros because we want our vertical numbers to add up to 6. So now let's say we have one positive real zero. And so once again, let's say we have 3 negative real zeros. So that's 4 now. So we still have 2 zeros left, so those other 2 must be imaginary. Okay, so we've run through our 3 positive options here. Okay, now, our 2 positive options when we have 3 negative zeros. So now let's say we have 3 positive real zeros, but now we have 1 negative real zero, right? Well, that's 4 once again, so we must still have 2 imaginary solutions or imaginary zeros. Okay, now let's say we have 1 positive real zero and we have 1 negative real zero. So in that case, we've found 2 zeros. So the other 4 must be imaginary, okay? And so that's how we can use Descartes' rule of signs to know how many positive or negative zeros or imaginary zeros that our polynomial functions are going to have.